So I'm Orri Erling from Meta. I'm a software engineer on the Velox team. Previously done every kind of query processing performance work, expert on TPCH, and previously worked at Google on F1 and built a thing called Virtuoso prior to that, best known for in the semantic web space, and now doing every kind of analytical data at Meta. So that's where I'm from. So let's move on to the talk. So this talk is about Prestissimo, which is our C++ based execution layer for Presto, and it's using Velox, which is a across-the-board query and query-like, database-like execution layer for Velox serves many different things. So first, we're going to be talking about the challenges. Why are we doing this? What are the environmental pressures that are driving this? And talking about what it means for Presto, what are the design goals and design philosophies that are driving this, a little bit about experience, a little bit about futures, some technical highlights. So I know we are late already, so without further ado, let's move ahead. So yeah. Okay, so data center capacity is at full utilization. Getting more of that is not self-evident. Even if you can buy more machines, you don't necessarily have data center floor space or power to power them, and applications just get bigger, and the environment gets more complicated. Regulation pressures, privacy, security add more requirements. Applications get more complicated. We are logging more data or having to do more processing, velocity increases, all these problems that the world knows about. So then under these, let us say, evolutionary pressures, we built Velox, which is an attempt at unifying a query execution and anything similar to that. So we have lots of systems internally, the stream processing, ETL, compute engines, Presto and Spark, diverse reporting-oriented engines, and they all do some kind of mix of query processing. And of course, them being implemented separately, they kind of do the same thing, but they're a little bit different. So there's a lot to win in terms of user experience, in terms of maintenance load, in terms of performance, in unifying that. So these are some of the motivations underneath. Now, we are deploying all that gear in the interest of Presto. Prestissimo is one implementation of Velox, one way we are using this. Okay, so we can do the next one. So the Presto Challenges is, like I said before, things get more complicated. We have new requirements. And while the data gets more complicated and data volumes grow, we got something running, and we need to keep it if it's interactive, we need to keep it interactive. If it is batch, we need to keep data landing, pipelines finishing on time and data landing on time for the users. And then when we approach peak utilization, we run into reliability issues like we get GC storms in Java and so forth. The closer we are to the peak, the more flaky it gets. And so therefore, efficiency is not purely a matter of seconds and dollars. It's also a qualitative matter of user experience. And then how to do that? Well, can you optimize Java? Can you do anything in Java? Well, I mean, if you have a single loop that you need to optimize in C++ and Java, well, I guess you can get the same instruction mix in either. But with Java, your abstraction becomes a void pointer, and it's you have to go against every rule and every convention, every good practice in Java to hit that. And that means going against the grain all the time, and winning 2% at a time doing this is not very attractive. So this is why C++ is kind of more naturally conducive to what we're trying to accomplish. Okay, next one.
Yep.
So what does it mean for Presto users? It means that you can run pretty much the same workload on a half or a third of the gear. So this is a whole new lease on life for you, and the savings in data center cost and so forth. And besides, in the bargain, you also get better latency and more consistent performance. we see, for example, we see that performance, as you add more threads to the CPU, performance tends to scale more linearly in C++ for reasons of GC and things like that. And we can better program for memory locality and do other optimizations. So in certain workloads, we see, we run on a third of the equipment, we get better reliability, better, 95 percentile response times, no GC storms. And in some cases, we got like 10x better latency. Of course, mileage varies depending on what you do. And of course, we build for the cloud like everybody else. So meaning the principal attributes of cloud as storage is remote, and then it has long latency, and then to go to have more drive performance, you need to stage data. So caching in RAM and caching on local SSD are, of course, important things. So then it is open source. Prestissimo is meant to be open source. It is not yet generally available. If you're an early adopter, it is possible to get access. We have a bunch of cooperation partners like Intel, HANA, ByteDance who already have that. And if you're passionate about this stuff, then you could ask for it. Okay. So architecture. It's not surprising. We have the same Presto coordinator we all know and love, and it talks to Velox over the Presto protocols. So the coordinator doesn't even have to know that it's a C++ worker. So in the interest of time, let's go to the next one. Okay, so powered by Velox. So Velox, like I said before, it's our attempt at unifying all query execution and query-like execution. So this means AI data preparation, stream processing, ETL, pretty much everything, anything where you do the same thing on a lot of data. And what do users get from it? It depends on the user. Presto gets efficiency. Other users who are already on C++ might not get a lot faster, but what it gets is consistent semantics. So if you have all the function library, all the data type support that you have in Presto, you have it everywhere, including streaming, AI data pre-processing, ETL, all kinds of reporting systems. Then that is obviously a huge win for the user. And of course, there's a win for the organization in terms of you optimize just once and it runs everywhere. And also you just maintain it just one time and it is deployed. So you can go deeper if you consolidate all these things because the requirements are going to be, from application to application, they're going to be very similar. So what we do is vectorized execution. So columnar-wise, we optimize all kinds of cache locality and prefetches and things like that are well known in the literature. We are embeddable and extensible, have been embedded in many places already. Like you can access Velox at different levels. So in one case, you fill in query plans and files. That's what Prestissimo does. In some other cases, you might feed in vectors and get vectors out. You might feed in rows and get rows out like Spark does. So a different way, or you might just use it as a library for vectors, a bit like Arrow. So then for Presto, obviously, Presto alone is not carrying the cost of maintaining all of that. There are also other users, which means it's likely to stay around, and it's also likely to benefit from contributions and being optimized not only for Presto. So there's a broader base of use cases that's driving its development, and that's only good for participants, in this case Presto. So then Velox, as opposed to Prestissimo, is open source, so you can just go and get it. And we have partners on board like Intel, HANA, ByteDance, and so on that are actively contributing, and you could be too. Okay. So for the Presto ecosystem, the question we often get is, okay, fine, what about the long tail functions? What about the long tail connectors? There's a ton of stuff for Presto. So we have 90% of the commonly used functions in C++, and we migrate them as use cases demand. For the long tail, which is several hundred functions, especially Facebook specific or Meta specific business logic, then this is planned to be served by a tier of Java Presto servers. And then if it gets hit a lot, then we migrate to C++ on a case by case basis. For the long tail connectors, there's like 30 odd connectors, and we are optimizing for the warehouse, meaning that we optimize for reading org files or Parquet files in some cases, and that's our primary point of call. For the other connectors, we plan to make the Presto coordinator make a plan where you have a fragment boundary between these long tail connectors. So they run on Java, and then there's a shuffle, like we'll connect between languages, or a shuffle barrier. So shuffle and then C++ on the other side. So this will take care of that. So next we go to what are the design principles. Like, you know, a lot of the world has found that the perfect query plan is an elusive goal. They've been at it for 40 years and they're still not perfect. So people like BigQuery at Google and Snowflake and others have found that adaptivity is better. And adaptivity is actually nice because then your data kind of tunes your processing. So we are betting on adaptivity, especially since we are serving multiple front ends and we don't control the query optimizer necessarily. So we must make do with the plan that we get. And so we can adapt in things like filter order. A good filter is one that drops a lot of data and that takes no time. So this is a good filter. We run these before batch filters. Same thing, hash table is very important. You know, hash join and group by, they all use that. So based on data characteristics, you can sometimes use an array and sometimes, you know, the normalized key and different things. So we adapt to that. Then of course, there's Presto has tons of knobs, like tons of session variables. So we try to not depend on that so much. There's fungibility. We don't want to be in a world where you say we allocate 1 gig for cache and half a gig for query intermediates, and this is divided over 20 different slots. This is much too restrictive, and DBAs no longer exist on one hand, and even if they existed, they wouldn't get it right. So the system knows best. So it means fungibility, which means intelligent, you know, resource allocation. Some goes to caching, and you know, cache gives way to query intermediates, which give way to group bys, and you spill as late as possible and stuff like that. So then the other side, information. You know, if you want to play nice, you must be aware of what everybody else is doing. So this means that operators can know about memory pressure. Presto is very good at logging a ton of stuff. We have no lack of stuff to log, but it is less good at actually taking action based on this information that it has. So here we try to do better by making this information available so that operators can make choices of batch size and when to spill and when to prefetch and stuff like that based on the availability of resources. So okay, some highlights on specific operators. Table scan is, of course, the #1 operator in lots of analytical workloads, and we have a very clever table scan that uses a SIMD to decode org files and uses SIMD to run multiple filters, you know, a single filter of multiple values, project out multiple values at a time, and so forth, AVX2. And then what we, of course, we can reorder these filters. So a good filter, again, you know, drops lots of data very fast. So we run these before other activity. We can push down aggregation into scan, meaning that when you decode the data, you, instead of copying out the data, you actually update an accumulator, and it goes that much faster. And then, of course, complex types are central to these workloads. You have lots of lists and maps and structs and things. And there, if you have, you know, 4,000 keys in a map, which we often do, and your query uses only 5, there's no point in, you know, materializing anything except the 5. And then there's some I/O considerations, like in all these workloads, we have lots of splits to scan, and we know ahead of time what we're going to be doing, so you might as well get going with it. For example, meaning that you can open files ahead of time and parse metadata ahead of time, read the file schemas ahead of time. They don't take a lot of space. You can keep a few of them around while you're processing the previous ones, and it cuts down on latency. Okay, the other highlight is hash table. I mentioned that briefly. So, you know, array-based aggregation is a well-known thing. We have the same hash table for group by and join. So it means that, you know, if you have a group by that works as a build side, then you just make one hash table and you can use it. And so that's one thing. Adapting based on data properties, making different data layouts and stuff like that. So we do all that. But of course, with SIMD sometimes vectorized access always, meaning that since you know what you're going to be hitting, you can as well prefetch, and then the hash table layout is like F14 or Google Swiss table with use of SIMD and stuff like that. So they're the things that you would come to expect. So IO stack next. Okay, so lots of people who do caching by quantizing the data into 1 megabyte chunks, and then you keep a certain selection of those around. And that's nice because they're all the same size and it's convenient. What we do is we cache by logical elements. So null flags of a column is one entry, and the values of the column is the other entry. And then, if you have lengths, that's another entry. And this means that we can recode at the logical level. So the cache might not be a physical copy or a piece of file, but it might be a re-encoding of that, and that gives us a bit more flexibility and optimization room. Then we cache first in RAM, and then we spill from that to SSD, and it's immutable data, so it's kind of safe to do that. And then cache, of course, is the one that will first give way, because evicting from cache is going to result in you having to reread data, whereas spilling a group by is going to mean that you have to write it and read it back. So group bys take precedence over cache. And then what you do when you got memory allocation, that's always different sizes. What happens if you're not careful, the fragmentation will kill you. And here what we do is we do magic with mmap and madvise to basically have an arbitrary size mix which can shift with time and does not fragment. I mean, it's others do that too, so it's known to the science. Okay, so trends. We are not existing in a vacuum. We have things that we need to know about and prepare for. Velox is built for the ages. So there's things like cache coherent accelerators coming on the. There's things like remote memory. There's things like an increasingly deep memory hierarchy. CPUs and different levels of RAM, or local and remote, and SSDs and disaggregate storage typically. So you need to be more mindful of the order in which you read your data and when to plan ahead on reading the data and things like that. Basically, the query optimization problem gets more complex because you have lots of devices that can, in principle, run your thing, and they can run it at different places. You have this business of computational storage, computational memory, and this interacts with data representations. So we are in talks with the usual suspects, like the makers of Arrow, Intel, ByteDance. CWI is where they invented a lot of the column store stuff, so they're good friends of us. So these are the futures for which we're preparing, and this informs our actions in today. Everything gets more heterogeneous, everything gets more fungible, everything comes out of a pool. You have lots more choices, and so you have to be smart, and your search space becomes bigger, so to say. Okay, so we go to experiences. We have been running diverse workloads. Quite often we see typically queries get 5 times faster, 6 times faster. Doing diverse interactive workloads, we are shadowing lots of. We have a ton of course, perfect benchmark. We got a ton of workload in house, so we are selectively shadowing these and taking on more and more. And we keep seeing wins of 2 to 4x typically across the board. Mileage varies depending on what you do. It's in the process. It's all underway. So far, it's very encouraging. And of course, we're doing a similar thing with Spark. So again, this is not only supported by Presto, but has applications beyond. Okay. So now I think we're kind of making it. So any questions at this time?
We do have a question here. I just see it now. I'm echoing. Okay, good. We have a question from Xing Quan. And it is, can you share the link to the open source repo? Is that possible, Orri?
Yes. So the Velox open source repo, we have the link in the slides.
Aha.
So, okay. So Velox is available today from GitHub, and Prestissimo, which is the Presto hookup to Velox, is available for selected partners. And if you want it right now, there's a possibility of getting that, and it would be generally available in first, second quarter, something like that, as part of Presto DB, and that exactly the manner in which and the date when is being formulated as we speak.
Cool, Orri. Well, thank goodness for Tim Meehan, because he came through and just put the Velox GitHub into the chat, so we're good to go on that at least. And Xingchuan, you can ping us at the help desk or whatnot and follow up if you need any help. But I believe all of this stuff is open source, so we'll make sure when we share the recording later that there's some way for you to get what you need as long as it's publicly available. Do you agree, Orri?
Yes.
Okay, spectacular.
For interested parties, they can contact us, and we can see if they want to work on Prestissimo. It could be arranged, but it would be case by case.
Fantastic. Well, this is pretty cool. We're really happy that you presented this for us. Thank you so much. Are there any other questions that people would like to ask? Or anything else you'd like to leave us with today to make sure that everyone's excited about?
Right. So to recap, we can make existing resources go a lot further. We can be safe, reasonably safe against future trends like future changes in architecture and so on. We have a lot of incentive to keep up to date with that, and we have a capacity to do so, and we have use cases to drive that. There's PyTorch integration with Velox, which is very, very exciting, a project called Torch Arrow, as AI is becoming the main consumer of data processing. So therefore, integrating with machine learning is important, and is one of the driving use cases. And of course, we are looking forward to like a co-evolution of a compute, meaning analytical data processing as we know it, and then AI algorithms. And maybe we can optimize the whole chain of training and inference together with data. So we get like an extended space of query plans, if you like. So that's one thing that we're interested in the future. And then right now, in the present, we're just working hard on onboarding and testing and seeing compatibility and verifying that we work and we deliver on existing Presto workloads. So this is all underway. And we hope to accelerate making this as well as a Spark implementation of Velox available to the public, so that public can see it and can contribute. The Spark team is working with us likewise, not to forget, as well as many in-house teams. So this is cool, and then of course contact us, and as everybody, we're hiring, and so.
Yeah, that's cool. And
yep.
I was just going to say, I mean, in my time in open source community building and management, I've had the pleasure of working with like Python and PyTorch community, ML and AI. And I love that tangential kind of huge community, multifaceted community that's going to come out of your collaboration there.
Right. Yeah. I mean, we talk to them daily. I mean, they're looking down the line, they'll be our biggest user. And right. So it's an important thing.
Right on. Well, if there's anything more you'd like to say, you still have some time. Otherwise, thank you again so much on behalf of the Presto Foundation and PrestoCon and everyone in the room.
Okay, wonderful. It's been a pleasure presenting to you.
Thank you.
Thank you.
Okay.